Hi, in this video, are we going through now basic topological notions so that we can introduce ourselves with more generalized forms of analysis in the context of more general spaces, and at the end you will understand better why we introduce this notion and when we can use this notion when we do, and it will help us understand real analysis a little better. So let's start off now with these basic topological notions, and the most basic, of course, is understanding what is a topology. So given so we know some if we are given a set and we give it a addition and scalar multiplication, then we call this a vector space. A topology is now a set consisting of now a subset of the set. So this is an element of the power. This is a subset of the power set. So it's like a collection of subsets of X having the following property. So in this subset, this subset is known as a topology. The empty set and the whole set are inside it. And this subset is closed under union of any other sub-collection and closed under finite intersection. So if you remember our video about metric space topology, we have introduced the notion of metric space and we define what's an open set there. And then we proved that this definition leads to it being closed under arbitrary union and finite intersection. But so now we generalize that and we abstract out those properties to form this thing known as a topology. So that this specific case in metric space topology that we generalize from, this specific case the property still holds if we use both definitions. So now instead of defining the metric space topology first, we define a general topology. Then we let these notions hold. And so with these notions, then we call the sets in these subsets that fulfill this condition open sets. And so using this terminology, one can say that a topological space is a set consisting of a collection of subsets of X known as the open sets, such that the empty set and the whole set is inside, and such that arbitrary union and finite intersections of the open sets are open. So an example we want shown here, where if we take a set, we can have many different possibilities of a topology. Our topology could be just the whole thing plus the empty, the whole thing plus the empty plus one singleton, or just take this. And you can see, so when you have a set, you can define different type of topologies on it. And you can see now that a topology isn't unique. So you can define different type of topologies on the same set. And these are the examples of non-topologies, because if you take the union of A and B, it will be this bigger circle, but that is not an open set. More examples and more known ones with common names is known as the discrete topology. And the discrete topology means all subsets of X is an open set. So you can think of it as you just choose which subsets you call open, and as long as they are closed under arbitrary union and finite intersection, then that forms a topology. And the trivial topology is the one where it just contains the empty and X. And I'll leave it to you to see online what is the finite complement topology, but it's basically meaning you X minus your open set, this is finite. And so when we are given two topologies in a given set, if let's say T prime contains T, then we say T prime is finer than T. Yes, I know it might be confusing to say finer, but later we'll give an example to suggest why we say finer. And if T prime is the one contained in T, then we say T prime is properly contains T, then we say T prime is strictly finer. And when we say T prime is finer than T, we can also say T is crosser than T prime, or strictly crosser. And T is comparable to T prime if and only if either one of these is true. So why we say finer is, you can imagine we have pebbles, and if we want, so if T prime contains T, it means T prime has all the open sets that T has and more. And so if you have a pile of pebbles and the pebbles represent an open set, to have more pebbles, we need to smash the pebbles into smaller ones so that the collection of open sets become enlarged. Because the maximum number of open sets you can have is the power set. So this is like fixed already. So this is like all your pebble. Like, so any pebbles before that will have been formed by very large pebbles. Then you have to break them up into the smaller sets so that it forms this big, and so it becomes finer in a sense. Another way to say it is that the topology is larger than or smaller than. So now let's just prove things about topology so that we get a better sense of what it is. And the first one is this thing where we just take a family of topologies on a set. So for example, you have the indiscrete topology. So that will be one form of topology in this family. And then the other one maybe is the discrete one, where it contains all the sets, the power set. Then we take an intersection of all these topologies and we say that it is still a topology. So for example, if you have the discrete and indiscrete, the trivial, then the intersection will still be the trivial one, and that is still a topology. So we say that the intersection of all these topologies is also a topology, and that is not really very hard to prove because the sets in one topology will be closed under intersection, and the sets, it will also be closed under union, and so it will still be a topology. Now, say we have, so this works for any family of topologies. We have proven that the intersection over this family of topologies will also be a topology. So now let's say we just have a random subset of X, or collection of subsets of X. And so what we want to do is gather all the topologies that contains this subset. So we are saying that this subset, all its elements are open sets. And so we gather all these topologies, the family of all these topologies, and then we generate, and then we say that a topology is generated by this gamma. So also can be written as T bracket gamma. If we take the intersection over this family of topologies that gamma is contained in. And so this is the smallest topology such that every member of gamma is open. So I hope you understand, and we have already proven that this intersection will be a topology. So we can say it's a topology generated by gamma. And so let me repeat the idea. Is like you have a set of X, and then you just take a collection of the subsets. Let's say again you take L empty and X as the subset, and then we gather all the topologies that contain it. And this means all the topologies every topology will contain empty and X. So this family is all topologies possible. So when you intersect over, you again intersect over the trivial topology, and that leaves you the smallest topology, which is the trivial topology, which says that empty and X are open. And so that is all for the introduction to basic topological notions. I'll continue this journey into topology for a while, and while I go through it, you'll see how it plays a role in real analysis. So I'll see you again, and I hope you like, share, and subscribe. Bye.